The second part of our video today is about the effective structure on the acid-base properties. So we have certain factors that determine the characteristics of acids. So the first thing we're talking about is this HX bond. Alright, so we have two things that go into determining the strength of an acid. We have the strength of the bonds and the polarity of the bonds. Okay? If the bonds are strong, then they're going to be reluctant to break even in solution. So if we have a strong bond, they're not going to break apart. So they're going to stay together, right? It's going to be reluctant to break, which means it's going to stay together. And we know that when acids stay together, that makes them weak. Okay? And if the bonds don't break, then it can't become more acidic because you can't get that dissociation. Right? You can't get those hydrogen ions in solution, and so it can't be very acidic. Okay? So stronger bonds equal weaker acids. Now we talk about polarity of bonds. We have a high bond polarity, right, that tends to increase the acidity of the hydrogen ion and make them very soluble in water. Now why is that? Well, that's because water is polar, right? So if you think about water being polar, and if we have an acid, right, it's going to be attracted to this negatively charged end of our water. If it's very polar, they're going to have greater attraction to each other. Okay, and so that will make the strength of the acid higher because it will dissociate more. Right, so a high polarity will give us a stronger acid. Okay, so if we look at, for example, why is HCl an acid but CHCl3 is not? So here we have what CHCl3 is this, right? And so our HCl is this, right? So why is this hydrogen not acidic? Again, it has to be able to pull off. So an explanation for that would be that this bond may be stronger, right? This bond may be stronger than this one, right? But for sure we know that this is a very large polar bond, right? This bond here is very polar because chlorine is very far to the right on the periodic table, which means it has a high electronegativity, whereas hydrogen has a low electronegativity. And so the polarity here is much greater than the polarity here. Okay, so this one is more polar, and therefore gives us this strong acid. Okay. And this one here is not nearly as polar. Okay. So now let's look at another example. Why HF is not a strong acid, but HCl is. Well, if we think about that concept of polarity, right? HF would be much more polar because fluoride is the most electronegative, whereas chlorine is still very electronegative. It's just under fluorine, but it's less. Okay? So in this instance, what is it that makes HF the weak acid? Well, it's actually the strength of the bond in this case. In this case, it's the strength of that bond between H and F that makes it want to stay together. It's a very, very strong bond. So in this instance, HF has a much stronger bond. Okay. So again, what questions you'll have for this are going to be more like giving you information about them, like they might give you bond energies, and then ask you about what would not it would be an acid or not, or which would be the stronger acid, or it would tell you which one it is and ask you to defend or explain why. Okay. So then we have another type of acid. We have what we call oxyacids. These have oxygen in them. Okay. So if our X element here in the middle has a high electronegativity, then the hydrogen will tend to be more acidic. Okay. Again, where are the most electronegative elements? Remember, those are N, O, and F. Right. They're towards that top right. These are our most electronegative elements. So if we look at that we have a high electronegativity, then these are going to be more acidic. And the reason for that is, so let's say we have HF and O, right? So because of this attraction here with the oxygen, right, that's going to, and the fluorine is going to be more electronegative than the hydrogen. Those electrons are going to be closer to here, and that's going to allow this hydrogen to escape away and become more acidic. Okay? Now, if A has a low electronegativity, then the compound tends to be basic. Okay? And that what happens there is we end up with a hydroxide ion coming off. Okay? Instead of the X element and the O sticking together and eliminating that hydrogen, the O and the H can stick together and that OH comes off. Also, we know the more oxygens that are around the X, the more acidic the compound, right? So, again, that has to do with the fact that if we have more oxygens, you're going to have stronger connections between this electronegative element and the oxygens, and again, that's going to allow those electrons to be pulled this way and that hydrogen to escape. Okay. All right, so then finally, the last piece of these notes today are about whether or not oxides are acidic or basic. Okay, so if we have a non-metal oxide, such as sulfur trioxide, comes into contact with water, it will form an acid. Okay, and then basic oxides are formed when we have a metallic oxide of group 1 or 2, and they react with water, and they form bases of hydroxide ions. Okay, calcium hydroxide in this case, and potassium hydroxide in that case. Pretty much that's really all you need to know. You don't even really need to know how to form the acids, but generally speaking, they just kind of all add together. There are some exceptions to that, such as in this case, but again, you don't have to know how to figure out which acids. What you need to know is that if it's a non-metal oxide, that it would form an acid, and then if it's a basic oxide, it would form a base. So if I were to give you a problem, and I would say you had a like Cl2O, right, and then we had, say, BaO, right, and I would say which of those was an acid and which of those would form a base. So this would form an acid because it's a non-metal oxide, and this would form a base because it's a metal oxide. And that is literally all you have to know about that. Alright, so we'll be looking at problems dealing with these in class tomorrow.